Aujourd'hui, j'ai mon point à 17h0, something like that. Parce que vraiment, dès qu'on découvre la film, on commence à taper à 16h50.
I have tried to post the tonight.
I said that just after that is done, I'm just straight. The discourse is done. Yeah, I'm sorry about that.
Yeah, it's okay.
Yeah, we didn't. Yeah. I would come to bed like yeah, or something like that. It's I don't know. I just feel late. And then I got lost in
Okay. Today in multimodal interaction, fusion and fission. So, okay, so first I will go to the fusion and then the fission. Well, in the very first slides, a couple of words what these concepts are in the multimodal interaction. And then there are some examples. And I have been revising this content, or basically adding some examples and so on here. And this is quite technical from, well, at least the examples are quite technical examples of how fusion can be done and so on. And this is a rather challenging topic in the sense that it is by definition kind of very technical process and so on. So let's see, just ask me questions, and for different people, the benefits of this lecture might be quite different, but the most critical thing is for you to understand what these concepts mean, and well, it's quite obvious why they are necessary in multimodal systems, but still I think some of the challenges will be at least explained. So what is fusion in multimodal systems? Fusion means that we have multiple modalities. We have information coming from these different modalities, for example, speech and gesture. So for the computer, for the multimodal system to be able to process that information, use that information, it must combine information from these different modalities. It must fuse this information together into something. So if we have this classic example of put that there, user says put that there, user points at a couple of locations, then the fusion is what takes that speech and takes that pointing information and combines it to some sort of internal system representation. Somewhere inside the system there is some sort of command or logical message or something like that, which here is presented something that looks like code object C, set position X, Y. So part of this comes from the speech, the fact that it is moving something, and some of these come from the pointing, basically the object identity and the position. And here is another picture. So fusion is this fusion of two kinds of inputs, and then on the other side there is fission, which is the second part of the lecture. So then inside the system wants to say something, tell something to the user. Fission is the process which decides that, okay, the system will use speech and some graphics to present this information to the user, and it will display this part in graphics and this part in speech and so on. So there are those two parts. Inside the system, somewhere here in the middle, we have only this kind of logical presentation, some sort of interaction or dialogue management happens here, and then on one hand we have the user providing the input using the different modalities, and on the other end we have the system outputting the multiple modalities, depending of course on the system what sort of combinations we have. So To be able to do the fusion, the multimodal fusion system, fusion engine needs to process the different types of input from the different modalities. We may get very different information. If you think of this, put that there, we get the speech, which is basically, okay, this is one speech command. It's on some level it's text, and then there might be some language understanding after that, which indicates that, okay, it's moving operation. On the other hand, the pointing can be just continuous list of points that the user is pointing at on screen, for example. There is no clear starting point that, okay, now the user started pointing at, now the user stopped pointing at something. If there are objects, of course, we can say that, okay, now the user started pointing at that object, or something like that. But bottom line is that the fusion engine can receive very different information from the different modalities. Then it must use some sort of time-related information. So if we think about this, put that there example for, again, we might look at as a nice example how we might interpret this. We look at the exact moments when the user said that and when the user said there. And based on those times, we select where the user was pointing at those exact moments. This might not actually work very well in real life because we don't align our speech and gestures quite as precisely if we are communicating, especially very fluently. Like if you're talking to somebody else, you might say, okay, put that there. And by the time I have said there and finished that word, only at that time my hand might actually reach the final point. So something more smart might be needed. But the critical point is that timing information is something that the fusion needs to consider. Then we can see that, okay, there is deterministic and non-deterministic inputs. This refers to the fact that some commands, for example, if you think about speech commands, some command might always have the same effect. Let's say we have command shut down the system. Whenever the user says shut down the system shuts down. But then there might be some commands which depend on, for example, the other modalities or the overall context of the system. So that the meaning is only decided in the situation and during the fusion process. So we need all that other information to be able to actually tell what that is. So that's not non-deterministic input. And then finally, we have probabilistic input. So as was discussed, especially with speech recognition, these confidence scores are often included in the speech recognition results, and often you get n best list, like maybe 5 speech recognition results with okay, it was most likely this one, but it might have been this one or this one or this one. And if you have only speech, then, well, depending on the dialogue situation, you might be able to select the second or third item from the n best list. But now when we have this multimodal fusion going on, we might actually combine information from the different modalities, and based on that, we might find out that, okay, what the speech recognition thinks the user most likely said doesn't really make sense considering what sort of gestures the user was making. And therefore, we actually choose the one that matches best the gesture and the speech, where they are most compatible. And of course, both of them can have some probabilities. There will be some examples which hopefully explain all of these. So I have here put that there examples, a couple of different ones. So this is quite simplified. So basically what the pointing information, in this case, I imagine it would tell the system that, okay, basically a stream of pointing, but whenever the user is pointing at some object, then that is marked as a kind of separate event. So in this case, okay, first user is not pointing at any object, then the user is pointing at one object, then the user is not pointing at any object, and then the user is pointing at second object, and then again not pointing at anything. So if you think of that, there are 2 objects on screen. The user has been first pointing one, then the second one, and then taking their hand down. And from the speech, we can put that there. and confidence for the speech is good. User most likely said that. So this is very simple. So confidence score tells that let's go through the speech example. So user has said something. Now the speech recognition tries to find out what did the user say. And speech recognition, like many other many other processes, especially machine learning processes, are all these kind of probabilistic things that, okay, we find out that this seems to be a good match. So basically you can think of speech recognition that if you have very simple case, we have, let's say, just listening to different numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Basically what the speech recognition can do that, okay, this is what the user said, this is the sound. We go through all of these different options, 1, 2, 3, 4, 5, 6, 7, 8, 9, and try to see how well they match. And some of them match well, some of them match not well at all. But the larger the vocabulary is, more words we have to combine, more similar words we have, the more likely we have at least a couple of candidates which are all quite likely. So confidence scores tells how good match the result is. So if the speech recognition is very confident that, okay, now the user said 1, then it returns as the first result 1 with very high confidence score. And then there might be a second item that, okay, maybe the user said 4, but it's very low confidence score. And then it might not return anything else. But then if we have very large vocabulary, we have, or user is not speaking clearly, or there is some background noise, or whatever reasons, all the people speak different voices and so on. So because of all these, we cannot for certainly say in speech never that, okay, user definitely said this. And yeah, so the confidence score gives us the best indication the system has that, okay, how confident the speech recognizer is that this is actually what the user said. So this is something to remember, so that always when you have speech recognition, you can never for certain know what did the user say. And this is also from the error management point of view. It's when you're thinking of how to manage the errors, it's very easy to forget that, okay, you can never know for certain. You can think of that, okay, if there is a speech recognition error, then we do this. But how do you know that there was a speech recognition error? You can never know that. You just get some confidence that, okay, probably this is what the user said, but then it might be that the user said something else, or it might have been just a dog barking in the background or something like that.
Can you design based on, like, design for the error recognition based on the confidence stage? Like, I mean, a confidence score, like, can, depending on the situation, if the situation change, then you get different kind of confidence score. Then can you, I don't know, design your interface thinking of it, if the confidence score is low, then this happens. If this happens.
Yeah. So the basic example is that, okay, if we have good confidence score, we do what the user said, or what the recognition result says that the user said. If we have rather low confidence score, we give a confirmation. Do you want to shut down the system? But if it's very high confidence, we shut down the system immediately. If it's medium confidence score, we say that, do you want to shut down the system? Then the user says yes or no. If it's very low confidence score, you maybe say that, okay, I'm not sure if I heard that. Can you please repeat? Yeah, so that's the basic example of how you can use the confidence scores. In practice, the challenge is that the confidence scores vary quite a lot. So for, as I said, we all have different voices, and our voices change depending on lots of different things, and the background noise and all this. So even the same user on different times of day might have good confidence scores at this time and not so good at that time. and so on. So it's not trivial to use those confidence scores, but yeah, it's definitely, yeah, error management is where it's useful. Yeah, so in this case, we have good confidence that user most likely said put that we have two different objects, and you can see that also the timing that, okay, when user said that, they were pointing at one object, and then when they said there, they were pointing at other object. So now the fusion can quite easily decide that, okay, definitely we want to move object O1 into the location where the object O2 is. Basic fusion, nothing complex here. Or, of course, the system which does this can be quite complex, because we can see next. Easily we have then situation where it's much harder to decide. So what if we have something like this? Okay, user was pointing at 3 different locations and said put that there. We still have good confidence that the user actually said put that there. Now it's still quite trivial. We just use the timing information and looked at, okay, most likely that is that location, there is that location. So we can still do the same decision. We can ignore this third one. Maybe it's what user was pointing, put that there, and then when they moving their hand away, they just happen to point at some other object there, for example. Then what if the fusion engine receives something like this? Put that there, but no pointing information. And in this case, we might have a low confidence score. What should the fusion engine do in this case? Well, based on this, it might reject the input, just decide that, okay, probably maybe the user wasn't saying anything, or the user wasn't speaking to the system. It was just some background noise, maybe. It's best to ignore. And it can do this based on the combination of these two modalities. One, that there is no pointing. Of course, you cannot put that there if you don't know where the user was pointing. And because the speech recognition confidence was low, then combination of those two information, they both indicate that, okay, this speech input probably has something wrong with it. Maybe it was mistakenly recognized by the system. If the confidence for the speech was very high, then we might give the user some sort of error message. Okay, I didn't see you pointing. Please try again, or something like that. Okay, we might get the n-best list from the speech recognizer. Maybe the speech recognizer heard put that there with very high confidence, but it also get the second recognition result, put that away, but also that with high confidence. So that it's most likely it's one of those. Speech recognition would say that it's the first one, but it doesn't say that, okay, the second one is fully off, and we only see the user pointing at one object. So now we can, based on the fusion, the fact that we have only one pointing, actually make the decision that probably user was actually saying put that away. So that if the user would have been pointing at 2 locations, then we would be able to choose put that there, because that would make sense. The combination of gesture and speech would match. But now, because only one location was pointed, we can make the assumption, which might be wrong. We are just trying to find out the most likely situation here, and we are kind of trying to minimize, and of course it depends on the system, but what we are trying to minimize or maximize. We might be maximizing to make it as efficient as possible, or we might want to minimize the number of errors the system makes, depending on how critical the operations are, for example. So these rules can then also be adapted based on what are the priorities of the system.
I wonder if there is any system that will provide solution for the confidence that is low, if it produces low, if people, if the user tries to speak in different slang, but still it's their English, it shows their confidence as low, and to rectify that? Is there any other tools or systems?
Yeah, well, obviously, most of the speech recognizers has been trained with native speakers. So, yeah, when, for example, I try to speak the English language recognizer, some of the words I have trouble. Then, of course, how the system reacts to that, it there can be some things. For example, if we see that okay, all the speech recognition confidence scores for this particular user are low, then we can accept. So if we have some sort of threshold here that okay, everything between here by default we ask a confirmation. But if a user always gets low confidence, maybe we move that low threshold lower so that the user doesn't get the confirmations all the time, so that the system is at least usable. It's well, extreme case of speech user interface is that you give a command, then the system asks you confirmation, was it this, and then you say yes, and then blah blah, and that gets really tedious, and nobody wants to use a system like that. So yeah, it's possible to do something like that. It's not easy to create such systems because then there is always the risk that okay, I start accepting wrong results, and probably if somebody gets low confidence scores, then there's probably lots of also incorrectly recognized results in that list. Yeah. Okay, but yeah, so those were a couple of different examples just to illustrate what sort of the decisions the Fusion engine must be making in stereotypical multimodal system. It's possible to implement the Fusion on different levels, and in the literature, the following 3 levels have been described: data level, feature level, and decision level. So here is an example of what those mean. So basically, well, data level means that okay, we are fusing the input directly on input stream level, and feature level that these feature streams that basically all these systems are using these things called features when they are doing the recognition. And then the decision level is basically what I just explained and what most of this material is about. So features, for example, in speech recognition, features are extracted so that when the audio sound comes in, it's actually split into something like 10 to 30, depending on the system, some systems 10 milliseconds, some systems 30 milliseconds, but very short segment of the speech. And then that is described with something like 30 to 50 numbers. So it's basically simplified to smaller number of numbers, and these numbers tells things like the fundamental frequency of the sound, so how high the voice is, then the secondary frequencies, basically how many different frequencies there are in relation to each other. This goes very kind of technical if you haven't worked with audio at all. But basically, features are kind of a small set of numbers which try to describe the sound or the image or whatever with a reasonably small amount of numbers, so that then when we are comparing because it's really useless if we just try to compare the audio files, the audio raw sounds, because as said, everybody speaks these differently. The sounds themselves are very different if you just look at the sound waves. So the features try to go a little bit in the higher abstraction level so that the comparison makes sense on that level. So features are used in lots of these automatic recognition pattern matching systems, and fusion can happen at that level, and then there's the decision level. So I have a picture of basically the example mentioned here. So if we have a speech recognition system where we have 3 cameras looking at the user and then 1 microphone listening to the sound. So basically the cameras are used for lip reading, and then the microphone is used for regular speech recognition. Now, if we want to create a speech recognition system based on that, of course, we must be fusing the information from these 4 sources, the 3 cameras and the microphone together, so that we get 1 output out of the system. So if we do the data level fusion, we might be combining these 3 video camera streams into 1 big image. In the extreme case, just put the pictures side by side, for example. And then after that, the video image is turned into features. The 1 big image is turned into a stream of features, which is used for the actual recognition. And then audio from the microphone might be turned into features at this point, and we do the recognition, or we might actually turn both into speech. Feature level fusion is that we turn each of these streams, the 3 video streams, into a stream of features, describing somehow the image with smaller amount of numbers, which help us recognize do the lip reading, and we do the feature extraction for the audio and get stream of features. And then there is this some sort of probabilistic machine trying to find what the user said, which uses all these 4 streams together. So this is feature level fusion. And then we have the decision level fusion. So we have a separate lip reading recognizer, another lip reading recognizer, 1 regular speech recognizer, and the 3rd lip reading recognizer. So each of them operating on 1 of the cameras or the microphone. One of them might say that, okay, user says, hi, my game is. Another one, hi, my name is. Third one, bye, my name is. Fourth one, hi, my name is. Everybody produces a different result. None of them is correct, but when we combine and do the fusion on this decision level fusion, we might be able to come up with the actual correct result. And of course, in all these cases, the reason, of course, to use multiple streams is to get better results because we have more data. But yeah, this is maybe the most technical part of this, and only if you are kind of a pattern recognition or machine learning or signal processing specialist, then this is something that you will be actually implementing. Is here for you just to provide you some sort of generic understanding that, okay, this fusion can happen on different levels. But most of the stuff that I will be talking from now on is this decision level. So we go into the high abstraction level and basically already what I in the previous example taught already. So we work on the output of a speech recognizer and some sort of gesture recognizer and so on. Yeah, so decision level fusion works on this conceptual level. These modality-specific recognizers have done their work. Speech recognizer has provided us some words, maybe even some natural language understanding has processed those words into some sort of a commands. And similarly for the gestures, we might have some sort of recognizer which already has processed the gestures into some sort of symbolic meanings and whatever modalities we have. And yeah, all of them may provide n-best list, confidence scores. So most of these multimodal fusion examples you can find in the literature and practical systems. They work on this decision level fusion. There are different algorithms on how to do this actually in practice. Some examples will be there, and they will be, well, basically describing fusion engines in the literature, and they tend to be quite technical. So we are getting more and more technical, so don't panic if you don't understand the stuff coming up in the following ones. It's mostly to give you overall picture and rough understanding, not assuming that you would kind of be able to implement any of the following things that are explained. Yeah, but yeah, there are these frame-based systems. So basically, this kind of a thinking of form filling. Different modalities can fill in the different elements of the form, and then final filled-in form is the output. Unification is the technical term for when you have this kind of rules where you can put items and then you combine the rules, and finally you have this one nice structure with where all the items fit in. Procedural, so more state-based, we kind of have if-then kind of rule. Well, not probably written in if-then, but you can think of more like that. Okay, situation is this, and then if we get this input, then we move here, and then finally we end up here. We have something, and then of course different combinations of these. And as said, time information is relevant, and inside the system we can also do this in different levels. So we can have this quantitative information, so we provide some sort of timestamp, exact moment in time. You can think of that, okay, this date and this time is exactly when the user said this and on this time zone and so on. Or relative to something that, okay, 75 seconds from the moment the system started running, and then 79.3 seconds from the moment the system started running. These are quantitative, and then there is this qualitative, so basically saying that, okay, this happened before that, or this happened at the same time as that one, or there is, yeah, the start overlaps with the end of that one. There is some clear work on what sort of concepts we can have there, and that also, of course, makes it a little bit easier to describe some of the things if you go into that level. So overall, this fusion, not all multimodal systems, of course, need it. If we have a system where the different modalities just do different things, still multimodal, but we don't need to do any fusion. But in stereotypical, these put that there type of systems, we need fusion. And these fusion engines have been developed, some examples of them, which try to generalize this fusion so that you don't write specific program for each application to where you encode these rules, but fusion engine can be something a little bit more generalized. Some sort of configuration is given then into this fusion engine to put in the application specific information in there. So here is a picture of how a multimodal system can be seen from this point. So we have a user here on the left. There are some input devices, for example, microphone and camera, so speech and gesture tracking. We have the modality-specific recognizer, so speech recognizer and gesture recognizer operating on this speech coming from here, and the camera image stream coming from here. We have the recognition results coming out of these things. We can have the speech and best list with confidence scores, and for the gestures we can have something like list of the objects being pointed. The fusion engine gets both of these informations, and then it tries to come out with some sort of a result. Okay, put that there, system move object A to position 5.5. Then we have some sort of dialogue controller or interaction controller, usually, which manages the interaction overall, and this receives the abstract input. So that basically the idea of the fusion engine is that we can separate this from this, because as you have by now probably understood, the fusion engine is possibly a very complex system and needs to do lots of decisions. So if we can make it one box and one piece of software or one element of our software and separate the actual dialogue controller, which decides then that, okay, if user wants to move that object there, then what should happen inside the system, but what that actually means and how it works. And then this outputs some sort of abstract command that, okay, now we are moving the object A to 5.5, and that must be communicated to the user somehow. And then we have similarly Fission engine, which can split it into the different systems. So if we have two audio devices, we have speakers for the speech output and display showing, for example, in the put that there system, the graphics on screen. The Fission engine decides that, okay, I will use speech to indicate the user that, okay, this command was received. And it can decide that, okay, system should say moving to indicate that, okay, now we are moving the object. And then in the visual display, then the application should, the moving object should be moved in the new location and should be animated in 2 seconds, smoothly moving there. So the Fission engine splits the logical output into however many modalities we have. And then the speech synthesis engine, for example, here, and some sort of graphics engine, which realize these into the user who is here, and then again gives a new input to the system. And this is, of course, one example of how it could look like. In this case, we have 2 input modalities and 2 output modalities. Of course, we can have any number of combinations, and we might have a fusion on the input, but single modality in the output, for example, obviously. Then, well, here are a couple of long quotes, which I will not read from literature, but their main point is that also when we are processing this complex input, for example, speech, there tend to be delays in the system. The speech recognizer takes some time to process the speech. We don't get the results the very moment the user stops speaking. For multiple reasons, we might not be able to know that, okay, this is actually the end of the user's speech. We might need to wait for a little while to make sure that the user is not speaking anymore. But more also the fact that we just need to do a lot of processing for the speech recognition. And all the different elements in the system, they cause these little or sometimes longer delays. And yeah, the Fission engine must handle this. It cannot assume that it gets all the information the moment it arrives. So here is this example doesn't show any particular problem. It's just basically what can happen. Basically, put that there system. Okay, so the user says, put that there. This is the actual moment when the user starts speaking. This is the actual moment when the user stops speaking. We can have, and usually have this component called voice activity detector, which detects that, okay, now the user is speaking, now the user is not speaking. So when it notices that, okay, user started speaking, it sends the Fission engine information that user started speaking. And usually here is some sort of delay. Basically, first the sound card must record the little segment of the speech. It must be analyzed to notice that, okay, the energy level rised or whatever the information the voice activity detector is doing. It needs to listen to little part of the voice. It needs to do some processing, so there is some delay here. Similarly, in the end, voice activity detection might need to wait for a short pause, for example, in the end of the speech. When we are speaking, some of the sounds we say are actually totally silent. Like when you are saying the sound T, there is this moment when your lips are closed and you are not actually saying anything. There is a tiny silence in the speech, so we need to actually wait for some time, even if the pause is there. And usually we want to allow the user to have a short pauses when they are speaking. So from the moment user stops speaking, the time Fission engine might receive the information that user stopped speaking might be some significant delay. And usually the moment it receives the speech recognition results is even longer. But of course, the good thing is that when this result arrives, we usually have pretty good indication that, okay, time when the speech started was that and when it ended was that. And those tend to match reasonably well the actual time. So those timestamps are then available here. Similarly, for the pointing, we usually have some sort of delays But just thinking of how the system works and how it combines the information, it might have received the pointing information, but it has to wait for the speech to arrive, for example, for some time. Of course, it might be that, well, especially if we didn't have the voice activity detector, we were just waiting for this information, then it might not know that, okay, there is no speech coming. Then how long would you just wait for the speech input to come and then decided that, okay, there was no speech. And especially if the user's pointing could also be some sort of gesture which has meaning without speech, then you would be able to react to that only after you know that, okay, there is no speech coming. But the fact that we receive the information, we do usually have the timestamp information at this Fusion engine level, but the time when the input information reaches the Fusion engine is very different often than it is what happened here. So we definitely are not getting information immediately. Yeah. And then a little bit more about the confidence values. So as was discussed, those n-best lists with confidence values usually come from speech recognizers and other such components. And of course, if we are combining information from two different modalities, we can basically take the confidence scores, if they are like normalized probabilities between 0 and 1, just multiply those and see which combination provides the best overall result and use that one. There is an example in the next slide actually about that. If we just simply multiply, so take the product of the confidence values, we are making the independence assumption, meaning that one information and the other information are totally independent. They are not really linked, so that receiving one kind of information in real life, usually there is some sort of linkage between these different modalities. I don't have a really good example about that here. Of course, the feature level fusion would be kind of theoretically optimal, because on that level we would be using all the information from the different modalities together, and then also we could kind of optimally calculate the final fusion. But this feature level fusion is usually not possible, basically because you would require massive amount of training data. Already creating a speech recognizer requires like hours of speech, where there is actually carefully been annotated what has been said here, and it must come from different speakers and so on. So then if you imagine that you would be collecting record training information for put that there kind of system, you would need to collect hundreds of hours of people doing put that there operations there, and just collecting that data is basically impossible. And probably when you have multiple modalities, you need to collect more data than from a single modality-based engines. And we might not even have the kind of statistical tools to do that, the algorithms to do that kind of fusion, where we have different type of feature streams from different modalities. If there is this independence assumption cannot be held, so different combinations of different modalities kind of result in differently distorted probabilities of confidence scores, then you might have some sort of a pre-adjusted matrix of that, okay, if we get bad confidence from this and bad confidence from this, we actually add something to it because they support each other or something like that. Yeah, it gets very complex, but if you are interested, then there is, for example, one reference here. But here is a simple example of what confidence scores in Fusion might be. So in this case, let's think of emotion recognition, where we have a camera looking at the user's face, and from the camera image, we are trying to recognize what's the user's emotion. The system says that, okay, user is happy, This is the most likely result, 0.5 confidence. User is angry, 0.4, or user is sad, 0.1. Might be sad, but not very likely in this moment, at this moment. And then we have speech recognizer, and then we have some sort of sentiment analysis. We are trying to analyze what the user said and try to find out what it tells about their emotion. User said, probably user said, I'm sad. Again, confidence 0.5. User might have said, I'm mad, 0.4. Very little difference in those phrases, so we are almost as confident about those, but I'm sad is just a little bit more likely, or I'm bad, very low confidence. So camera says most likely happy, speech says most likely sad. We multiply the scores, okay, happy, because the speech didn't say anything about happy, we get confidence of 0, so that actually together we think that happy is not possible. Sad, we get the low confidence from the camera, so we get very low confidence together. Angry, we actually get decent confidence from both of those, so actually the angry is the most likely based on the 2 different modalities. So the separate modalities told one thing and the other, but then when we combine, we get the most likely as something different from the both of those.
Do you know if the accuracy of combining modalities in fusion, is it more accurate usually than like single modalities? Or?
Yes, yeah, there is various indications that we can improve the accuracy when we are using multimodal information. That's one of the listed benefits often that, okay, why to do multimodality is that if we use different modalities, we can be more confident what the user is actually trying to do. Well, for this kind of examples are maybe the most clear, so we are just trying to understand something, and of course if you use different kind of information sources, which all of them can provide some reasonable information, then combining that information can be much stronger than individual modalities. Of course, there is always the risk that, okay, we have one recognizer which is really bad and gives us wrong results. It's really confident, but it's making the wrong decision. Then it would be better to just remove that from the system. And of course, yeah, lots of testing needs to be done, but that's definitely one of the potential benefits of multimodality, that we can be more confident about what the user is actually doing when we use different kinds of information sources. And you can think of yourself as an example. So most of us human beings, at least, we can understand each other better if you think about noisy conditions. You talk to your friend in the cafeteria with lots of things going around. If you look at that other person and listen to them, it's easier to understand what they are saying because you can see the lips moving and you get some information with your ears. If you just want to try to listen to them, it's harder actually to understand. And well, for most of us, especially just trying to lip read, it's very, very hard. But together, those 2 modalities supporting each other can help, and you can try it out next time you have hard time hearing somebody. Try to look at their face when they are talking to you and then try to hear what they are saying just looking at something else. And there is also this thing called McGurk effect. I don't remember if it's mentioned somewhere in the material, probably very briefly, but it's an interesting example of how we human beings do this multimodal fusion. So it can be, if you just Google McGurk effect, I'm sure it's mentioned somewhere in the materials, but you can find these YouTube videos illustrating it. So basically, it's that you hear something, person saying something, you see their picture saying something else. I think the examples are like T and P, so something like, yeah, somebody saying T, and video, they are doing P, and actually what your brain thinks is that the user is saying, the other person is saying D. So something in between. So your brain is fusing these two different modalities and trying to make the most likely, basically what we are doing here. We have information from two modalities. One modality might by themselves be saying this, or the fact that is that the audio is this and the video is this, but the brain then decides that, okay, most likely it's this thing in between, because, well, it doesn't work on those concepts in the brain level probably, but still, this is what happens. You get something, you experience something in between.
Sorry, how do you spell it?
Let me see if I can. Yeah, McGurk effect or McGurk illusion. So, yeah, as you saw there already, there were videos illustrating this and explaining the phenomenon and so on. So you can study that if you are interested. Oops, I think I jumped into. Yeah. So now I have a couple of examples of different fusion engines that have been created over the years, basically in research institute trying to create nice multimodal systems, and then finding out that, okay, this fusion is so complex that we need to probably have a dedicated component to do that, and then have created this. So as you can see, for example, this one is very old, basically from the time when this was first possible. Melting pot is the name of this one. It's using this back Amadeus architecture. This frame-based approach, which there are some images which hopefully help understand it. And there are these, they use these terms lexical level, syntactic level, and semantic level fusion for the kind of 3 different levels of processing. And yeah, they use the dialog controller for that central module, which was on my picture. It was dialog manager on the right. Or well, basically as part of the fusion in their system. And they use this software agent. So basically the program is split into small elements, small pieces of software which all do separate things. And these agents actually run in parallel, and they receive some input. This agent might be doing part of the fusion, and here another agent is doing part of the fusion, and then when third agent combines their result. So these microfusions are done by these agents, and they use time and then the structure of the object. So as you will see in the next slide, it's basically this kind of a grid filling elements in there. So here basically we have input from different modalities, and it's put into this kind of grid. So put that there example is used here again. So we have pointing information here, pointing information here, speech, put that there. We have these agents here working on this information. First fusion happens in here, so these are all the agents. This one combines that these two into this object, put that there, so this object will be put somewhere, and from here this editor decides that, okay, this pointing is actually indicating a position, and so here on low level it was just user pointing at something on screen. And in this fusion, it was decided that, okay, this pointing is selection and this pointing is position on screen. And I think here the vertical in this grid indicates the temporal aspect. So this was pointed first, and then this was pointed second, and then another agent combines this into this final form. So this object will be put there, and this is the temporal order. So basically, trying to put the information from the different modalities into this one grid-like structure, which communicates the final information. And because it's using these software agents, it can provide immediate feedback to the user, even before the whole process has been gone through. So each of these agents can provide some feedback to the user, provide something graphics on screen, or provide some tiny segment of speech, this back channeling type of information, aha, for example. So while this is processing the information, the output that was generated by this one could already be displayed to the user. And then the central dialogic controller is modality independent, as has been seen in the discussion earlier. And the melting pot, the melting pot is this structure where the information goes into. So it's this 2D structure, kind of a form. And different parts of it. So columns are basically different kinds of information that can go in there. And time information is included in there. And when all the relevant parts of the melting pot object are filled, then that's the final result. And then, of course, if we get information into the same slot of the melting pot structure from different modalities, then that can tell that, okay, user has been indicating the same information twice, or it might really inform us that there is maybe something wrong. Maybe we have interpreted incorrectly some part of the input. And then there are these different levels of fusion, the microfusion. Basically, overlapping events can be combined there. Macrofusion combines information that are happened close to each other. Then there is also contextual fusion, and it checks for this redundancy mentioned earlier. So it does that on if you get two information at the same time, it checks for that. There is another example of flights from Boston. So this is a system where you can speak and then click on the display. User clicks Boston and says flights from Boston. So we get the Boston from into this slot where it could go into the, and then, well, basically we just in this case assume that, okay, user repeats him or herself and flights from Pittsburgh to this city and selecting Boston. So here is how the form might look like in this case. Yeah, so that was one example. Here is another one. I will come through it similarly fast. And as said, these are mostly just to illustrate some sort of approaches how this challenge has been done. And there are lots of technical details which we cannot cover and probably won't be very fruitful to cover. This uses things called typed feature structures. And unification, so two terms which, if you start looking at this kind of issues deeper, you might encounter these concepts also in other cases. So both of them are used in many different users. They are not specific to this Quickset system. They are just, Quickset system is just applying these concepts. And hopefully the both will be explained. So here is an example of feature structure. So it has a name. Name of this feature structure is create unit. It consists of two features, object and location. And then those features, object feature has type unit and location has type point. Object then again has features, so it can be recursive structure. It can also be at one point empty, so the location doesn't have anything inside it at this moment. And the basic idea is that using these feature structures, the different commands and different inputs are modeled. And then here, what you might have in the beginning, okay, user has said that create here a tank platoon. So this is a speech. It will be turned into this kind of feature structure. Create unit, recognized from speech. This comes from the tank platoon idea. And this comes from the fact that in the system configuration, there is definition that, okay, create unit always has location. So we didn't get the location from the speech, so it remains empty. At the same time, user clicked on these particular coordinates. So from there, we get this generic command feature structure, which contains location, and it has the data here. And so we have location here with type point, and the feature structure create unit contains location with point of type point, and that's empty. So basically what we can do now is to put this here, and then we end up with the final result. We have the complete command create unit tank platoon in this location. And yeah, you can think of then you have lots of different of those features, one matching like every possible command there is. All the input is first mapped into some sort of feature, and then this combination. So basically what happened here, what the animation showed you, is the unification. So you take two rules, and then you either have a kind of a leaf in the bottom of one structure where it's empty, and then another one can be put there, or the other way around. They can go either way. Or unification, you can also have such that you have kind of this long, if you think it as a tree, you might have a node in there where you actually put something new so that it becomes the child of this part, but also the bottom part becomes the child of them. The one, well, depending on the system. But yeah, so the unification just tries to, it goes through all these different possibilities how you can combine these feature structures together, and basically usually if it's well-built system, there is usually one possibility how they all match together, and that's the final result. So of course each so if you just basically trying to indicate a point, the system might actually interpret both that, okay, there was a point and there was a line, so it creates two feature structures. And then during this unification, so if you think of this case, for example, we would have a location and we would have a command line, then only the location can be put in here, so then the location would be used and the line would be ignored. So unification process then can find the best matching one. And in this case, of course, if there are multiple interpretations for one modality, we use only one of them. And it uses the timestamps as well, but I don't have any detailed explanation of how this happens, except that, well, on generic level, it requires that speech follows the gesture, and here their work is that is usually 3 to 4 seconds. So user points at create tank platoon here or delete this object. So there is this 3 to 4 second time, and then they build in that rule in there. And also, as mentioned here, they wait for a couple of seconds. Even if the gesture is a full command, they wait for the speech for a couple of seconds so that they know that if there is speech or not. And basically, that's multiplying the probabilities here and can apply a threshold. So if a combined interpretation has low confidence, reject it. And of course, it's possible that you end up with, if you have n best list, you can have multiple final. You use the confidence to choose the best one or reject all of them. Quickly, third example, this is something that I built. We work with Mezzo for today, Valmet automation to create a window management system for to be used in, or it's also a demonstration system. So they are building systems for factory control rooms where they often have these big shared displays, and we created this prototype of how user can go there and point at the screen and say that, okay, show alerts, and then alerts window opens there, and you can grab and move windows, and you can point at the window, and if you're pointing at the window and say show alerts, then alerts are here in that window, but if you're pointing at an empty area, then a new window is created. And you can point at the window and say next screen or things like that. So basic window manipulation and speech-based access to these different displays. The average power plant or factory has maybe have something like 100 different displays which can be shown in there. So speech is actually quite efficient way to access that large collection because they all have names and people know those names. So yeah, you can do this basic, close this window, next view, show alerts. And I wrote a simple unification parser. So it takes the raw ASR text results, combines speech and pointing. And pointing here was basically IDs of the windows that have been pointed. And then we used very rough grid coordinates so that the windows could be like was it like 4x4 grid coordinates so that we not have very fine coordinate system, but pointing basically moving very rarely. So basically we have information of the currently pointed window and previously pointed window, and that was all that was needed. And grid coordinate if the user is not pointing at any window. And yeah, if you're looking at the literature here in this kind of parsing thing, often you find them bottom up and top down. So this is bottom up parsing. So we start by finding meaning for individual words, basically in speech. Top down would be that, okay, we have this one global rule which would explain everything, and then we start to split the sentence into these parts. So this is bottom up, we find meanings for individual words, and then we start to combine those together. And basically in the system you could say that configure it with this kind of Python code, but you can say that, okay, if this piece of text is fine in speech recognition results, it means that, okay, we create this action close structure so that we create this combination of command, or the fact that this is an action and this is close. Or if the user said alerts, then it is name with value alerts. And then we have this higher level parse templates. So these are used to find out the low level meaning for individual words or combine a couple of words in the speech. And here we have the higher level rules. So if we have action close, or we can put action close here, and then if we have current window pointing, we can combine those into one structure. Or if we have action close and name, and none here means that any wildcard matches here. So basically here, this generated name alerts, this can be slotted here. Okay, we can create. So if user said close window alerts, it would match this one. So because we found close, action close, and we found name and something, name alerts. So user can just say, okay, yeah, close window alerts, for example, and that's perfect pointing to do that. So here is this is a little bit simplified or adjusted example, but another example how it works. So okay, we have this name alerts, and then it's fusion rules, action show, action open, name none, so this can match this and this. And then we have third one item, we must have the user currently pointing at window, or in the second rule, currently pointing at position. And then from the pointing, we have get either this or this. If we match this rule, we get to fill in this one. So this is basically given here. So in the first case, if the user was pointing at the window, we have this current window pointing from the gesture, we match this rule, and in other case, we match this rule. And this is basically then go into the dialog manager, so that in the first case, it knows that, okay, I need to display information in the window that's already open. In the second case, I need to open a new window and then display there something. Yeah, and this means that when we have enough of those rules, depending, the same input can have these different meanings depending on what other modalities provide information. Very simple history in the pointing, and it just goes through all the different combinations on these rules, how you can combine things. And then, of course, you need some sort of dialog history if you want to allow something like that. Something like user saying close that, meaning that, okay, the window we were previously talking about. But then, few words about this fission, multimodal fission. So this is the other part of the process, how we construct multimodal output. And this has been split into 3 different tasks. One is content selection and structuring. So we decide actually what we want to communicate to the user. So the central dialog manager might give us very high level abstract information. And then we might assume that, okay, we don't need to tell the user about everything that we can tell. User probably remembers something and so on. Then decide the modalities that to be used, and then construct the actual message. What exactly is said, what exactly is shown on display, whatever modalities we have. In most multimodal systems, of course, this is rather simple process, and this is just hard-coded into system logic or something like that. Area where most of this fission and related work has been taking place is in this embodied conversational agents. So basically you have 3D character, animated 3D character on screen, or it can be 2D character who's speaking. So you have speech, and then the character is also doing gestures, both and facial gestures. And for them, these different markup languages have been created for describing how this kind of a character should behave. So basically, the multimodal fusion engine can output this kind of a. There are also some more generic markup languages. These haven't really become too popular. This is still very much something research units do, and when somebody commercializes it, things are made much more easier than things is. But the concepts here are kind of relevant. So this first example is affective presentation markup language. And both of these examples, they have these elements they call performatives. So, well, there is text that the system says, could you just please mind your own business? And I will mind my business. Let's get on with our lives. And overall, on top level, there is this performative. It's indicated that, okay, now the system should be suggesting something. And of course, this example, at least in the paper where I looked at this, they have these potential values: info, ask, read, or request. And obviously, suggest is there as well as this example. So of course, if the system is asking something, it can use different tone of voice, different bodily, so on, if it's suggesting something or reading and so on. So providing kind of overall information what the system is doing. And reams here are telling that, okay, which part of this are new information. So for example, when I'm lecturing to you, I sometimes hopefully remember to use my tone of voice to indicate that, okay, this is the information you should now pick up and understand. And now I'm just keeping myself talking to lead you to the next topic. And now is the important part. So green indicates that, okay, this should happen. Should be somehow given some sort of emphasis. And then there are these tags for particular strong emphasis, how to do that. FMLAPML is another quite similar language. It has quite long list of performatives, so it's using the same concept of performatives in flow order, suggest, propose, warn, approve, praise, so on. So you can see the actual text is here on different part, and it's split into these FML and AP or PML parts. So this is the speech part, and this is more about the meaning and behavior of that one. And there are these indications here, indexes, which are used here that, okay, there is a person indicated, and it's actually myself. So if you imagine this is an animated character, it could say, hi, I'm Poppy, and like point to itself based on this information. And it uses this SSML, speech synthesis markup language, for the speech. So as well, it's not using any of that here, but SSML allows also you to do emphasis and this kind of things and change the voice of the speaker and so on. Okay, but I think those couple of quick examples are all I have on the fission. And as said, this is probably the most technical topic of the course. And very few people in the world are actually building this complex or complete fusion system and fission system. So this is more to hopefully make you realize what sort of issues there are when we want to actually support this kind of multimodal interaction we human beings, for example, do with each other. It's far from trivial to try to do this combination and understand this combination of different modalities and so on, but also that there has been decent amount of work in this area. So well, maybe the most important take-home message is that if you end up in a situation where you would be okay, I now need to create multimodal fusion, you know that smart people before you have already thought about this and worked on this, so you might stand on their shoulders rather than try to build it from ground up. And yeah, for fission and for this, so now you have an exercise on multimodal fusion, and as I have added some comments into the template, I'm not assuming you to be able to define completely how the fusion would happen in the system of yours, but hopefully you take one example from your earlier designs where there is multimodal information and just think through. You have well, about 1 day worth of time thinking about this and identify whatever aspects you can and figure out what sort of complexities there would be in implementing such system. And some of the systems might actually be quite straightforward, no these complexities that I discussed today. But the most important thing is that you spend some time thinking and realize that, okay, this looks easy, or this what I designed is actually very complex when we start looking at this level. And I also created, I haven't had the example solution for you for the last couple of exercises, which I think has been good decision in the sense that it's probably good to have for a first order, maybe a couple of first exercises, but now that I haven't given you example, you have much more varied ideas and approaches maybe than during the very first one. But this time I have included an example there because I was thinking that this can be quite daunting task, maybe trying to think about this. So any examples about this and what sort of issues can be there is probably helpful. Well, I hope that example is helpful. But let's see. And I haven't written any feedback yet for the earlier exercises, but it is definitely on my to-do list. So at some point soon I will hopefully have some feedback on speech exercise and then gestures soon. Okay. Unless there are any questions right now. Thank you. See you next week. And we will hear some presentations, I think.
Are you actively doing some Android development? Because I can see from here. So,